So we have spent a considerable amount of time talking about how we acquire images and what different modalities are. And essentially, no matter what imaging technique we are using, we're going to have some noise built in. And noise and errors. So noise is essentially an error in recording or interpreting my image, what ultimately ends up as a grayscale value in image. So we consequently have to also figure out how to try to remove some of that noise. Okay? So that's often referred to as filtering. There are different names, but we're going to refer to grayscale image filtering, and we're going to do some of the we're going to do some of the exercises today that are kind of very common. So after we have learned how to acquire and reconstruct the image, we essentially need to do something with it. We're not here just to looking at images is just fine, and learning from images or seeing or attempting to see what's in there, but at the same time we need to quantify in order to compare. So any kind of quantification will require what we refer to as image processing. And before we process to get quality output or something that we rely on, we need to try to remove noise as much as possible. Okay? And then after that, we're going to try to then recognize phases with our image and do segmentation. So filtering in itself is information loss. We just want to lose the noise, right? But it's nevertheless information loss. So if you have a very good image, and this is an example of very sharp image, this is a backscatter, SEM backscatter image, then technically if you filter this, you're going to spoil it. So just because filtering sounds cool, that doesn't mean that it should be applied all the time. You should technically look at your image. Now, if you have something like this that is very noisy, you almost have no choice. Because quite frankly, a lot of algorithms that come after, if you don't filter this image, they're gonna just stop and not work. Okay? So you kind of have no option if you have a very noisy image. Now, this is just a joke, but essentially, filtering is image loss, and that's what we often go for when we Photoshop photographs. We're losing small details that some of you are not old enough, but some of us are getting older, so we want to lose all of the details that come with age. So again, filtering is image loss, but let's put it as a targeted image loss. All right. So when you have a low resolution image, this is nothing really replaces taking image at a resolution that is high enough to actually get what you need. So when you have pretty low resolution image, things appear smoothed out. Okay? And trying to basically get information from this can be problematic. And when you have high resolution, it's much better. Often you have to kind of look at your histogram we already commented on that, to gather what is your image quality. Okay. Now, in the previous information loss that we refer to as photoshopping, if I was trying to remove wrinkles from my face image, right, I would basically filter and blur intentionally to remove those fine lines. If those fine lines were actually microfractures in my image, such as, are they visible? Yes. Okay, this is essentially a little microfracture. If I filter this image in any way, I'm going to lose this microfracture image from the image. Okay? And if I'm looking for fracture, that's a bad idea. So you do have to look at the image and decide what it is that you want to do. Whereas here, well, I couldn't see fractures to begin with. But in order to actually process this image and discern what is my solid face from my porcelain, technically I have a lot of ring artifacts here. This is from X-ray. And those appear almost like mini fractures, except that they're not real. So those I want to lose. Okay? So this is this, look at the image and decide what do you want to lose from the image or not. So in this case, I want to smooth out so I can process later. So I want to lose this small information because it's essentially noise. Small distinguishing characteristics here are not noise. They're actually real. There's a mini fracture through this grain. Okay. So you have to decide what it is that you want to lose. So that decides whether you want to filter or not. Now, there's not just filtering, but there's also basic image transformation. So we're working on a grid. That grid, the way images go, is always sort of a Cartesian fixed grid. If you want to do anything with the image, like rotate, you have to do essentially a mathematical calculation to rotate that image, right? We know how rotation works. We have formulas for it. But once I rotate something, I am now not aligned with my original grid. And because I'm not aligned with my original grid, if I want to now represent that as a new image, which is still on my original grid, I have to kind of figure out what are my values I need to interpolate in order to get the image, right? Because the moment I rotate, let's say that I rotate something with any angle that is non-90 degrees, okay? So I rotate by 30 degrees. My rotated points will not fall on the regular Cartesian grid of, let's just image my projector. Like this is an image and it's obviously pixelated here if you get close. Okay. So that type of transformation will lose some information depending on how you do that interpolation. So you have to be careful with that because with images we are always on this finite fixed grid and it's discretized. And when I do anything to it, I might lose information. So if you are given a choice of interpolation, go with the more accurate one. Typically cubic, bicubic, or cubic splines are a better way to interpolate than just linear. Okay? So when gauging values in between points and you need to fill them in, you're going to somehow interpolate in between. Go for more accurate if you can stand that computationally, if it's not taking too long. So let's actually do that. So we're going to open, there's a rotation example, and we're going to actually see how we lose information. And just before we go into that, so what we're going to open an image. Then we're going to duplicate, so we have like 2 copies of it. And one of them, there's a transformation, there's a rotation by 45 degrees. And in these points where we need to estimate what my new image is, we're going to use bilinear interpolation. And in second example, we're going to do bicubic to see the difference. And then we're going to rotate back by minus 45 degrees. So I'm going to have 2 rotations, right? So technically, when I rotate back, I should get the same information back, except that it's not going to be the same because I lost some information in that process, okay? And we're going to measure how much we lost by using image calculator, which can subtract 2 images so we can see the differences. Yes? So is the procedure clear? So just to actually estimate how much information you lost, and then we're going to repeat the process with bicubic interpolation. All right. Image J. Open up. So this is a portion of that sandstone image that I saw, and I will blow it up. So plus blows things up. Okay. I'm going to say 45. So 45 is not aligned with the grid. And I'm going to do bilinear. So you can see how when I rotated, well, these pieces I lost in that rotation because I'm not aligning with the original grid. And these have gotten filled with. So there's some definite loss in the corners. And now I'm going to rotate back by minus 40. And okay. And what did I say that I was supposed to do? Do duplicate, which I didn't. So now I have to open it up again. All right, so this is my original. So I have obvious loss in the corners. Okay. But I can also see that it appears slightly blurred. Look at the sharpness. Here and here. If you look at your screen, you will see. So even visually I can see. Okay. But we can do image calculator. So I'm going to subtract them. And do 32-bit because if you get negative numbers, you're outside of your, possibly you're outside of your range. So it's the safest thing is to get a float result. Plus interpolation also introduces values that are in between your. No. My. Oh, it got hidden. So you can see the differences. And as I'm walking around, so this is minus 22, 10, so even up to 20 or 22.7 to 10, right? I could do a histogram of this, just actually see what the differences are. Now let's repeat for bilinear. So I, again, will do now I will be a little better about creating a duplicate. So now I will rotate, but I will do bicubic. And then I'm going to rotate back. So it's definitely sharper than my previous. Rotate and rotate back. Let's see the differences. So the range of values is that I'm definitely not going to 20, but I am going to plus minus 4. Yes? So it's still there, just not as much. And of course, where I suffer the most is where I actually have changes in my values that are bigger. If I'm moving around within only solid phase, I'm relatively constant. So those constant values will not change as much when I rotate and rotate back. Whereas near the edges of these two different phases, I have a pretty high jump in values, and that's where I'm going to see this. Okay? If I'm in business identifying these edges, then of course this is we're going to accumulate more error, so that might be something that is important to think about. Yeah, everybody got a chance to try? So any kind of image manipulation could be image loss, because your image starts on a fixed grid, and if that manipulation, such as rotation, actually moves it off that grid, and I have to estimate values on the grid, which is interpolation, then try to do that interpolation as accurate as possible. So bicubic is typically offered in menus, but that's what bilinear versus bicubic is what you should be going for. All right. Excellent. So that is our first exercise. So this is just to show the way. Okay. So this is my original image, rotation with bilinear interpolation, and rotation back and forth with bicubic. So this is bicubic is better. Now, often with any kind of filtering of the image, there is a word convolution that is used. Okay? Now, convolution mathematically, when I'm convolving functions f and g, okay, this is in one variable, I will take a shift from the value, and I will shift this g around a certain range of values. Okay? And I will multiply the two and then integrate. Integration is summation. Okay? In two dimensions, I'm going to have a double integral, right? And I'm going to go over a neighborhood that is in both coordinates, right? So our images are typically 2D, right? So I'm going to have a double integral here and shifts in both directions. Now, when it comes down to the image, if I'm walking over the image, what this integral is really is summation of discrete values. Okay? So you will often have something that is called a kernel associated that is basically representing this this function you're convolving with. And I'm going to do a little example of this in a very simplistic way, but basically that's how a lot of filters work, and they can be expressed in such case. So let me just change. So let's say that I have an image in a very simple image. So the simplest image I can ever think of is 3 by 3 in this case. So this is my 3 by 3 image. Okay. And actually I have some values in the image. The best I can ever come up with is 1, 2, 3, 4, 5, 6, 7, 8, 9. What else? Right? So my image is essentially a function in two variables, x and y, right? Discrete function with discrete values, 3 by 3 values, right? So you can think about it as a function in two variables, so my r of x, y, if you will. Okay? And now the way I'm going to represent this convolution, and often it's called correlation. Correlation and convolution are really just rotation by 180 degrees of each other. So we're just gonna assume that they're the same for the practical purpose. So I need a kernel, so-called kernel. So I'm going to use correlation, convolution, kernel. And kernel can be any size, but since my image is 3 by 3, well, I cannot be bigger than 3 by 3. So I'm going to use an example 3 by 3. And I'm going to do any numbers. So this is my another, so when I'm convolving two functions, right, I'm taking a shift and I'm basically just multiplying corresponding values. And there are certain coefficients that are involved. And the second function, g, f convolve g, is also some numbers that are evaluated on this same grid, right? So I'm going to, for a very simple case, use 0, 0, 1, 1, 1, 1, and 0, 0, 0, 0. Okay. So in this case, if I'm going to convolve, I'm going to take the value and I'm going to, so my convolution result, okay, is I'm going to place this kernel, whoa, so I'm going to center kernel window over a pixel value and just integrate, which is a summation, and do sum in both values, right, of my, so kernel, I'm going to call it g, I of x, y, okay, and this g of x plus shift, let's say a, and y or minus plus b, plus or minus, that's what basically gives me correlation. And this a is going from, in this case, minus 1 to 1, and b is minus 1 to 1, right? And that's, so I have values minus 1, 0, and 1, that's 3 by 3 then, yes? So this is basically, summation is my integration in discrete case. So if I do that, what I'm going to replace here, when I center at 5, I'm going to, my x value that I put will be 1 times 0 plus 2 times 1 plus 3 times 0. So I'm just going to do corresponding, if I assume this kernel is placed centered at value 5, okay, I'm just going to multiply corresponding values within that window, okay? And that's essentially this thing here. Plus 1 times 4 plus 5 times 0 plus 1 times 6 plus 7 times 0 plus 1, 8 times 1 plus 9 times 0, right? And what it really is 2 plus 6 plus 8 plus 4, right? Which is 20. So my convolved image will have here 20 in the middle. Now technically I should be able to place this kernel on every, this is a very simple image, my 3 by 3 image, I. So what I do with the, technically I need to pad this image. Just like in any numerical scheme, I'm missing values on the boundaries. So to really fill up this convolved image, I'm going to call this y. To calculate y, I need to pad original image on the volume sides. Right? Which is what I need to do anytime I'm doing any kind of, for instance, discrete version of a differential operator, right? I need those values near boundaries. So I can fill them in with zeros. I can mirror, so I can put here 1, 4, 7, 7, 8, 9, or whatever here. So 7 would go 1, 2, 3, right? I can now choose what to put. And that's, then I would take y. So for y, I would get then 4 plus 1 plus 5 plus 7. What is that? 12 plus 5, 17. Right? After padding. Now, pretty much any transformation I want to do on the original image, I can find sort of a kernel that represents it. If I'm calculating, let's say that I'm calculating derivatives, right? What is a derivative in x direction? Assume this is x direction. What is the central difference that gives me derivative approximation? I of x plus delta x minus I of x minus delta x divided by 2 delta x. Yes? Central difference. Can you come up with a kernel that would give you that when placed? Approximation to x direction derivative. This is when I mysteriously press the little button. Anyone? The only delta x I can do in this image is 1, right? I mean, I could do more. So this is a shift plus 1, shift minus 1, right? And then I have to divide by 2. Do you see it? Gonna let it sink in. So what would be x direction derivative at this portion here? It would be this value minus this value divided by 2. And divided by 2. And that would be placed in the center in a convolved image. So convolution with this kernel would give me central difference in x direction. So every derivative has a little kernel expression like this. Ultimately, you're doing something, you're computing on the neighborhood of the center using surrounding values. That's what you're doing when you're estimating derivatives.
So when this is I x plus delta x, it means we are referring to the u sense.
Yeah, this is my, that's why this is my x direction, right? For y direction, I would get this and that.
So it would be 6 minus 4 divided by 2.
Yeah.
So it would be 2 divided by 2.
Assuming the result is
right. This is a kernel that I need to do that. So if I now convolve with this kernel in the same case, I'll get 6 minus 4 divided by 2. Yes? Or rather, 1/2 times 6 minus 1/2 times 4. Yeah. So pretty much any transformation on the image is going to involve some combination of the neighborhood values. Second order derivative is just going to have a 5 by 5 kernel, because I need more, right? So that's why convolving an image is essential. Any transformation can be expressed as a convolution. And strictly speaking, correlation is just in this definition is taking a minus here, and convolution is taking a plus. But when I have a symmetric, this is a symmetric operator, right? So it's kind of the same. Then it doesn't matter. Convolution and correlation are the same thing. So the result of a convolution is an image, another image. So technically, all kinds of filters I apply are the result of a convolution operation, or I can find sort of a convolved operator that is going to go. Maybe median is not, but give or take, like basically filtering and convolving. Again, I'm pressing my mystery little button for and convolving image with a kernel can be thought of as equivalent. Okay. In future, I'm guessing, well, that future already exists, it's just not mainstream. As I write, I will be able to train AI to recognize my handwriting and immediately type instead of me writing, right? And then we will avoid my ugly handwriting. But until that future is here in mainstream, you have to somehow deal with my handwriting. Apologies. So again, a lot of operators on images. If you just think about it in a certain way, even if translation, right? If I'm translating everything by a pixel in this direction, I'm going to have 1 here and 0 everywhere else. And technically, expression of that shift is a convolution with that kernel. Yes? So a lot of things, anything that I do on an image, I can kind of come up with a kernel that expresses it. Okay. So often Gaussian blur or smoothing, which is if I wanted to remove wrinkles from my face or any kind of thin lines, that's a way to reduce noise, is typically convolving with the Gaussian function. Now, what would the Gaussian function look over 3 by 3, right? How does Gaussian look like? In 1D, Gaussian looks like this, right? In 2D, well, so now if I can think of a little hat, right? In 2D. Like literally a hat, right? By the way, now that U.S. elections are in full swing, one of the candidates, Amy Klobuchar, her last name is Slovenian. It comes from klobuk, which means a hat. So, whatever, they were hat makers at some point. So this would be klobuk, or a hat. Back to our club. So this, if I basically projected that on a 3 by 3 kernel, exact values we can debate what they should be depending on what this Gaussian is, but technically something like 2, 1, 1, 1, 1, 0, 0, 0 would be something as a discretized version of this, like I'm very high in the center and I'm low around it and I'm symmetric, yes? Can you see that? So this would be a 3 by 3 version of Gaussian kernel. Now, technically, you need to also divide this. If I'm normalizing, am I normalized and am I not normalized, right? I could divide all of this by 5. Or, yeah? But you get the point. So this is basically a discrete representation of this two-dimensional function that I'm convolving with. And I can also see that if I place this little window on top of a pixel in 2 dimensions, in 3 dimensions I would have a 3 by 3. It's just very hard to visualize that, right? But if I place that on top of a pixel, I'm going to say, well, okay, my middle value has the most importance, but please consider others around it in giving me this convolution. So if I was wanting to kind of normalize my image, assuming that I could potentially have noise in the middle, I want to consider the surrounding values too to even things out, and then just maybe normalize something back to the original values, okay? So that's essentially what convolution then can do. So then Gaussian function has some sort of Gaussian kernel signature, and this signature changes slightly. You can do that over a larger neighborhood. 3 by 3, 5 by 5, 7 by 7, and so forth. Often it goes in, if I want a center pixel, I need odd number. So 3 by 3, 5 by 5. But I could figure it out with 4 by 4 as well. It's just not going to be as, I might have like 2, 2, 2, 2 in the middle as my middle. Right? So that Gaussian function has some sort of signature in whatever kernel size I want to project it to. It's a little projection. And because I'm smoothing things, so if I smooth things and I have an edge and I take near edge, let's say that I have edge in values and I have values of 200 and close to 0 near that edge. If I'm taking into consideration everybody, for a value that is 200, I'm going to take into consideration zeros that are right nearby. And that will kind of reduce my 200s. So it's going to smooth out, right? So what was sharp is not going to be as sharp anymore. Now, if I was looking to remove wrinkles from my face, yeah, great. I don't want sharp vision for anyone to see them. But if I'm interested in characterizing those wrinkles, then I shouldn't do. So smoothing is bad if I'm looking for edges, right? So don't smooth if you're looking for edges. But if you want to remove and kind of even things out, then it's great. Okay? All right. So then, blurring convolution operations, they tend to make things look better because there is no noise. But that sharpness could affect certain features. Like if you're looking for edges, that can be problematic. So you have to know what you're doing, essentially, and what your ultimately objective is. Now, very common filters are mean and median. And mean, essentially, is a version of a Gaussian, really. But it's a version of filter where you're just look at all of the neighborhood values and take their mean and replace my center with that mean value, right? So if I was looking in this world, I would take 1, 1, 1, 1, 1, 1, 1 over 9, right? That would be my mean value. I have 9 of them, 1 over 9 everywhere, sum it all up, right? And that's going to give me a mean. I could also take, so mean is also possibly going to smooth things out, especially if I'm near an edge. And median is another way, is to just like order all of the values that you have within. That's not necessarily easily expressed with this kernel, but basically look at the neighborhood order the value and take a median of those values. Okay. And that can also, so basically outliers that way will get removed. Okay, and with median, it's a pretty effective to remove outliers, assuming that my noise is some random outlier. That should work well. However, when you take mean filter, if you take 1/9 and sum everything, then the result of that is not necessarily, if your image was values that were non-real numbers, so basically discrete values, then the mean result of it has to be rounded up to get back to, let's say that you had a 2-byte integer, right? So that can introduce values that didn't exist before, and there is a little bit of a step for doing that. And median filter will actually pick out of the existing values, which is useful. So I frankly kind of prefer median filter, so I'm not going to introduce, because I'm not going to introduce values that don't exist. But it stays some smoothing, so if you have a sharp edge, you might go on either side of the edge, right? So it's smoothing, but it's a little gentler than mean. So I'm going to remove outliers, but I'm still going to stay within. And of course, in all of these operations, it does depend what is the neighborhood that you choose, and it's your choice. So you can choose the median or whatever filtering in a 2D image in a 3x3 or a 5x5, and the larger you go, more smoothing you will do and more damage, right? So if you take too large of a kernel to keep my Photoshop reference consistent, you don't want to, by removing wrinkles, remove an entire eye, an eyebrow. But it depends on the size of the feature. So you need to know that there is an eyebrow and a wrinkle in an image, and that you have to stay within. And if you don't know what you're looking at, it's hard to choose the size of the filter. So there is bias or the choice of the person processing the image. So be careful, remove wrinkles, but not eyebrows. Let's do another exercise. So we're going to do median filter, and we're going to adjust it just to explain before. So we're going to open a sandstone, which is actually, it says sharp sandstone topographic slice, except that the image is not sharp. It's way sharper than that one. And then make 2 copies, and we're going to do a median filter and use the sort of the radius or range of 1 and 0.5, and just see, but to actually see what this mask looks like. So it has some sort of footprint in the neighborhood, and you can see the visual of that footprint. So median filter refers to radius because it's going to attempt to be circular. Okay, I attempted to be circular here. It's just in a 3x3, the definition of circle is very kind of square and edgy. Yes? So this is a circle in 3x3 world, in a discretized 3x3 world. So have a, yes? It's very kind of squarey, but that's the digitized world. So you can see what those masks are. Maybe we can actually first play with process filter circular masks. So my not so sharp image of a sharp sandstone, and duplicate. So you can first show those circular masks. So this is your 0.5 radius. That's precisely the one that I use. Okay. So that's, I have values that are non-zero here and 0 outside. That's my circle of what here is referred to as radius 0.5, 0.5. Now, frankly, I would call this radius 1 if I'm going from center of this pixel to center of this pixel, or even 1.5, but there is now almost a you could open up a philosophy club, which is why they have, they show this here as a radius 1.5. Now, if I go 1 up, so this is radius 1. 1.5, 2, 2.5, 3, 3.5. So these are my discretized circles. Now, if you had way more than 6 pixels across and you're looking at this, then eventually it attempts, it looks closer and closer to a circle. But those are my discretized circles, and that's the best I can do in the discretized world. If I'm just looking where circle is and where it's not. Now, what with time and technology, what increases is the resolution of your screen. So if your screen resolution was 100 by 200, all of the circles would look like this. But your screen resolution is, what's your screen resolution, do you know? Right? So all of the circles, they look circular, though that's simply because you didn't zoom in enough to see all of these little edges. Okay? So now smoothing anything with this radius would pretty much kill an image. So don't use the large radius. But let's now try to do median filtering with this. So mean or median filtering will now basically try to take into account whatever was shown as white is your neighborhood, right, of certain radius. So in the filters you use range or radius 1 or 0.5 to do just those closest values, but you can use larger if you do need to lose an eyebrow from that image, okay, then use larger. So let's go with this one. Image filters. It's, well, I need to ultimately process filters. Okay. Okay. So I'm going to choose first that 0.5. Okay. Okay. So you can see how that smoothed my image. I'm going to duplicate. And I'm going to do another. I used median, right? Mean. Okay, then I'm going to stick with the mean. I'm going to go. Okay. Then let's do median, just larger. Okay. See what happened here? Kind of starting to lose shape, and any kind of thin things will start to disappear. Now you can use, in this convolution business, you can decide, I think you can, here you can specify your own kernel. This is one example. You can kind of do whatever you want to do. Here you can type in a matrix and you will get that little convolution, okay? With the understanding that a lot of these operators, they can all be expressed with these kernels. Now, whoops, oh, there we go. I did that 24 and minus ones at once. I wasn't looking what I was doing, but here it is. Okay? So all of the filters, that's what they do. Okay? So all of the filters on your images, if anybody is using that, is it Snapchat? I'm a little behind. So all of these filters, they're just doing that, but also in color and whatnot. Yeah. So that's just for pointing out certain parts of the image, but typically smoothing works the best. But also you can do distortions of the image and you name it in certain directions. So if obviously if in that kernel you give it a preferred direction, you're going to get preferred direction, right? So shapes will suddenly start getting distorted. Okay? So all of these manipulation, and you can play here. You can do minimum, maximum, and so forth. You can look at the various. In 3D, to work on a stack and have the 3D version of these, I have to let the image J know. So those are 3D. So they typically have 3D labeled. Otherwise, they're working slice by slice. So be mindful of that. Okay. So if you're processing a three-dimensional stack and you do want to look below, above and below. Now, in terms of X-ray tomography, since we talked about it a lot, if I have X-ray tomographic image that has very good resolution, 2 micron in all directions, then I do want to take into account, because this arbitrary, this XY, what is XYZ is essentially arbitrary. Okay? So I do want to take all of the directions into account, and I do want to then do median 3D. However, if I have a CT image from the Carlos lab, and I have, like, let's say that my core is this big, right? And I'm taking slices every, what is this, 5 centimeters. Well, now don't do anything in Z direction. Don't take information from the up and below Z, because your delta Z is way bigger than delta X and delta Y. So you don't want to do anything, because you're going to take information that is far away from the point where you have, right? So in that case, I would filter in 2D. So you have to be mindful of how image was taken to decide whether you do 2 and 3D. And again, you can show this circular mask. And a lot of things that have a name, they're there because, so if you wanted to come up with your filter, okay, you can give it a name and you can create a little ImageJ plugin, okay, and you can give it to everybody as a plugin that has your name on it. Okay? So that's an option. So this is how these two came up. I don't know what they're about. I didn't try them. May as well now that I'm talking about the process. Again, I have no idea what they are, but I'm guessing it's used very much in some type of microscopy. Okay. I don't know what I'm looking at, but it seems that I have kind of formed some regions of smoothing. Yeah, so it seems that this is attempting to group pixel information in some little neighborhoods. Okay. So again, you can plug it in if you'd like. So again, filtering is image information loss. It's just that often we do want to loss. Now, take a try mean. Let's do the following. So I claimed that mean and median. That median is a little gentler transformation of the image, right? I just claimed that. Let's test it. I didn't do this comparison, so I hope I don't need to bite my tongue. But let's change, let's use the same radius, say radius of 2, and do a mean filter and a median filter with the same radius. And then do a difference with the original. And histogram the differences so that we can see. So test my claim. Mean versus median for radius 2. Do mean of image, median of image, minus image, and then histogram. So, is it true that median filter is changing the image less than mean? Is this clear? Why am I doing this way? So this is a way to compare, right? This in itself, these differences are an image that tells you where the differences are spatially, but I'm just interested statistically to see that these differences and we're going to take this as a quiz for today, so submit as quiz. And while you're doing that, I'm going to open up an assignment and throw that into a PowerPoint or something and give me some images and snapshots. Lecture 3. See slides. Or from February 24th. Difference between there we go.
First, we have to use the image calculator to subtract the two images.
And then you histogram them. So histogram gives you a summary of those values, right? And how many of which differences you have. Because this is otherwise a two-dimensional image, right?
So when I select histogram, it provides me the solutions, bins, and exercise.
Yes. So the differences are real values. So you probably give it a try. So for mean filter, okay, so this is one. So when you look at the list, you will see that standard deviation of these differences is about 25, right? So now try to do the similar thing. Was that mean or median?
This is mean.
Mean. So now do the other one.
So deviation 28.
So this one is a little larger, right? That's essentially it.
But when it says the mean value itself is pretty small.
Oh, okay, I didn't look at that. That's interesting. So part of it is this is an excellent point. Okay? So we have the differences. Did you all get something like this? So what is the cumulative difference? So histogram gives me sort of the point-by-point values and how many of them were in certain bin. Okay. So I have that I also have, so my minimum is minus 81 to 167. So my minimum and maximum are somewhat larger. So I possibly removed larger outliers in my image. Okay? But that's just minimum and maximum. Ultimately, there's not that many in this range. So if I basically overlap these two histograms, I wouldn't get that much difference because there's very little on the fringes, right? Now in the middle, I have a more continuous change for the mean and not so continuous change here. So what is my so technically I would actually probably need to sum up, do a list and inspect this. These are not normalized, so I don't know what is the count here. And I don't know what is the count here. So technically I need to know what are the largest values that I go here. I need to essentially integrate them there, not just look at the histogram. So maybe do a list. Let's click.
If we just look at the histograms, it seems that the mean is better, right?
It's smoother. That's all I know. Right. So it's smoother. So I get overall larger standard deviation. But what is my largest count? There's 27.
There's 198 too. There is 425.
Right.
573.
So I think it would be actually a very good idea to simply surround zeros. I have the largest values, right? These are the counts. But then I have this discrete peaks in here. Around 0 again. So this peak is very large, but then question is how does it compare cumulatively speaking? So I think I would have to integrate with the changes, the total changes to the image. Now visually, which one looks better to you?
Mean.
Mean? Because it's smoother? Yeah. But that I think depends on the feature you want to look at. No. So again, mean value will smooth out more. If you want to integrate under that histogram, that would be an interesting thing, and normalize. So I would integrate or overlap them to actually see the differences, but because of the discrete nature, it's still going to be hard to see. There are those sharp discrete peaks that show up. You're the jury, okay? So sometimes I'm doing changes to the image. They kind of look, possibly that kernel of radius 2 is simply A too large, right? So I'm possibly better off doing it on 0.5. So I'm doing too much changes to begin with. But question is, how do you want to compare? Is sometimes what is the type of outliers that I have in my image, and who do I want to remove? So it's not a clear result. So if you do list, you can save as .csv. .csv you can open up in MATLAB, or you can open up in Excel, and then you can histogram in those on your own. And that way you can do that curve on your own and process it and possibly overlay them, right? So I'm going to leave this quiz open. If you want to do that, I'm going to leave it open till tonight. So maybe just overlay those two histograms on top of each other to actually see direct. So these are the differences. Okay, one more point. So differences. So there's, if my difference is 0, possibly plus minus not a huge deal as much. So you can plot all of the values, all of the positive ones. And the least change I made to the image is if I have a lot of zeros. Right? Because the difference of 0 means no change. And it's the median that had the largest peak at 0. So with median filter, there was a lot of places where I didn't change as much, but overall, I possibly removed larger outliers. Does that make sense? So how do I compare for larger differences versus smaller differences? That's something interesting. I would actually map that histogram, save it in your favorite software where you process graphs or plot graphs. ImageJ would not be my favorite software where I plot graphs. So save that CSV. I would just look at sum up the absolute. So -1 and 1, same thing. It's a change of 1. Yeah. Or possibly take those differences, then there is an ImageJ way to do absolute value of an image as well, and then histogram that. These are 2 challenges for you to
the difference between like the new package and the package. And that's it, basically.
So again, we like mean filter because it looks smoother, but that's also removing more from the sometimes from the image. But it might be removing more in different places and removing less than median in different places. And it's a very good question, how does one evaluate that? One comment, and we're going to try to do this next time, but just to give you a look. So one would actually like to first identify, so in order not to change much across this edge of the image, I would have to know where the edge is. Okay, so that's called anisotropic diffusion. So basically I'm going to try to even out or smooth a lot on this side of the edge and on this side of the edge separately. But I gotta know where the edge is. Okay? So there is actually iteration that does that. What it essentially knows is like my large change is a large gradient. I know how to find those spots. Okay? So basically, in the presence of a large gradient, I'm going to try not to cross over that gradient and grab an image from the other side of the edge. Right? Grab a value. So you're smoothing and dataset along the edges, but you don't do minimal you do very minimal smoothing in grabbing values across an edge. Okay? And what is gradient physically? What does the gradient, when I take pressure, dpdx, dpdy, dpdz, there's a vector, right? The gradient of pressure is a vector. In a pressure field, where does that gradient point? So like say I have a z or a 2, I have x and y, just dpdx, dpdy. So I have pressure in two-dimensional domain. Where is the gradient of any scalar field pointing to?
Towards the peak.
Largest, yes, where the changes are largest. So gradient direction is the direction of the largest change relative to the spatial, right? So basically, if I know the gradient of an image, I also know where my largest changes are. Right? We use that for the largest change. So basically, where your magnitude of the change is the largest, that's possibly where the edges are. Right? So you basically evaluate magnitude of the gradient of an image. Image being a scalar field over x and y, just like pressure. Yeah? So that's the physical meaning of the gradient, and that can be used in these smoothing operations in order not to cross the edges, right? And minimally smooth across the edges and less so along. All right. Submit your verdict on a mean versus median by 11 o'clock tonight.